ahead.
Okay, so hi and thanks everyone for being here. It's the very last day before the holidays, and this topic about Git is something that I had the intention to cover for a few reasons. So first, it is important to consider who is this presentation for, because we know that Git is a productivity tool. It was born as a version control for tracking modifications of files. But why I want to underline that Git is not only for developers. So it is true that you can still work on source code, but you can also work on documents. You can also work on task automations. You can do much more than just editing files. And so what I am covering right now is the basics. So with some theory about how Git handles the modification trackers. And then I will also do some small demos about how do I use Git in the first place. So I think that you can also see me writing on screen. If that is true, it's a plus because I can make it a little bit more interactive. Do you see what I'm writing?
Yes.
Okay,
Yes,
so
they say
very good.
yes.
Yeah, thank you for for the relay. So now let's move into the main topic. So when we talk about Git, we consider a version control system. Why do you want a version control system? It is important if you want to record file changes. Also, if you want to collaborate and agree on whose modification should be taken into account. You may want it to recover from your mistakes and to tag some snapshots of your code that is maybe reaching a milestone, and then you want to use that to deliver your code, your document, or your system that you are trying to develop. Now, in the past, version control was very manual. You had to manually create a directory, maybe with your document on version 1, version 2, version 3. I think at some point in our life, we have all been there. So like you have your Word document and then you are writing a first version and you save it with the version 1, and then you copy this file into another directory, or maybe even in the same directory. And then you start having my doc v1, and then you copy it, and then you do my doc v2, etc. How many times this has led to errors? Well, for me, it was a huge number. And therefore, I started looking at some centralized version control systems like SVN. And SVN, it's the shorthand for subversioning. This control system was quite nice, actually. I used it a lot, even in Telecom Paris. In the past, we had our central server, and it started introducing not only the concept of collaborating, but also the fact of having a central version, so what we call a repository. And then we had multiple working copies, and we could work independently, and then we could just commit our modifications to the central repository. The evolution of SVN is what's called the distributed versioning control system, where you have an additional step, and each local copy can even include some collaboration capabilities, and we will see much more of that in the remainder of the presentation. But the topic was Git. And Git is not actually a version control system. Git is much more than that. We will see that Git is a version decentralized file system with native branching capabilities and integration with complex workflows. We will see that Git does not track changes like SVN. In fact, we will have a concept of snapshots. Git is not local only or remote only. It allows for complex workflows that can be adapted to different needs. And most importantly, Git is not linear. So Git allows for what we call merging and branching, and this in a very native way that is easy, that is mostly error-free, and as per usual, the main source of error is the human that is using the tool. But we will see how to minimize this kind of errors. So we will see that the main Git concepts involve the repository, the state of the file, branches, the interaction with both the local copy and the remote repository. And then I will also focus on, I think, the killer feature of Git and similars, that is the interaction with hooks that are basically scripts that can be executed on both client side or server side, and complex pipelines like the CI/CD pipeline that I use. So for most of the figures in this presentation, I used or I reworked some from the book by Chacon and Straub. It's a free book. You can download it online, and I think it's very exhaustive. It's really nice because it explains a lot of concepts with clarity. I will also be very interactive in the sense that at some point I will use my terminal, and I hope that that you can also see my terminal that I open here. I know that unfortunately the lighting in the room is not very nice, so I have this presentation mode, and I think that everybody can basically see what I am doing in my screen. So for getting started, you can already start with a repository in your local file system, or with an existing repository that we call it clone, that you clone it from a remote URL. So the URL that I presented at the beginning of the presentation was the URL of these slides, plus some additional things that I can show. And you can also start playing with Git in your local file system. Like you create a directory. I can go on TMP and TMP. I can create a directory that I call my project. I go to my project, and then I do just Git init. So the repository is initialized, and Git is very verbose with that. It is very verbose because it is saying to me, okay, you are using this, you are doing your global configuration is not active, your branch is called main, and then you see initialize the empty Git repository here. How do I see that my Git repository is initialized? Well, there is a hidden directory that is called .git. Once this .git directory is done, your repository is ready for tracking modification. So in particular, the Git directory will keep track of the config files, of the history of all the modifications, and even alternative histories. So we can start playing with the repository, but I think it's very important to understand the file model used by Git, because the behavior of the tool will shape how you interact with it. Now, there are two different philosophies on how to track changes in a file. The most common approach that was used by SVN was to store a list of incremental changes of local files. We call this delta-based control version. So what happens is that if I go to my external here, imagine that you have a file. The file is called a.txt. So once you have this file, you have some content. You have line 1, you have line 2, you have line 3, and this is your version of the file. Now, suppose that you are adding a new line, So this is the initial version. You add line 4. So your system will track a delta that is added line 4. And this is your file with this delta 1. Then if you do other modifications, you can also remove lines. You can change the content of each line. But basically, at each iteration, you have some delta, delta 1, delta 2, delta 3, etc. So your file, a.txt, at this point of time, let me paint a timeline like this. So this file at this point in time is just a delta 3 with respect to this delta 2, with respect to this delta 1, with respect to the original file that you have submitted here. So this delta process is the way that files can be reconstructed and that you can track the changes at every point of time. In Git, we don't do that. In Git, at each point of time, we do a full snapshot of the local file system. So basically, the content of all file is completely stored into a database that is inside the .git file. And therefore, at each version, you can retrieve the full copies of all your files. And for each version change, no reconstruction is needed. No interaction with the remote central server is needed. In your local .git directory, you can retrieve all the files at any point in time. So this is much more heavyweight if you consider the amount of data that can be stored. But in reality, this means that no reconstruction is needed. So you can switch from version 5 to version 2 almost instantly. In Git, you have a file system that stores all your files. Of course, if files are not modified, a pointer to the previous file will be stored. So there is no need to recopy the file if no modifications have been done. So a pointer is just used when files are not changed. But whenever a file is changed, the full new content of the file, like A1, A2 for file A, or C1, C2, and C3 for file C, all the new content and the old content is contained inside the object that is created by Git. Now, each version in Git, it's called a commit. And each version can be identified by the value of the commit hash. We will see that in the demo later. So the commit is the basic unit with which Git can reason about its state. And we say that you advance histories by making commits. So from version 1 to version 2, from version 3 to version 4, etc. You are making a commit, which means that you are keeping some files, you are tracking the changes, you are storing the full file, this full set of files that can be tracked, and then this can be retrieved at any point in time. So Git contains two different hierarchies. It contains references and objects. So the objects that we will see are the commits, are the trees, and the blobs. So blobs is the acronym of binary large object. So a blob contains actually the full content of a file, but not its name. Names and other directory structures are stored in trees. So a tree contains the directory structure and list of file names. And finally, so what a commit contains? The commit contains the hash value of its identifier, so an hash ID, a pointer to the, let's say, to the first level tree. So the first level tree that is your main directory that contains your file, and a pointer to the previous commit. So once we are here at the third commit, we have its hash value. We can use this to identify the specific commit that we are interested in. The first level tree, and in this first level tree, what we see is this directory structure. So this directory contains a file called new.txt, contains a file called test.txt, and contains another reference. This is a reference to another tree that is itself a tree that is a subdirectory. In this subdirectory, there is one file that is called text.txt. So basically, we can see that now each file can be identified by its name through the tree where it is contained, and the blob contains the actual version of the file. So for instance, here, from the second commit to the third commit, no modifications have been done to test.txt. So the blob didn't change. We can use the same blob, and we can just update the reference to this file test.txt that on the third commit is still at its second version. And these are all the objects that Git stores inside its .git directory. Of course, we need some way to facilitate interaction with Git, and for that we use references. So a reference is a pointer to a specific commit. Here we can see that there is a master reference that is pointing to the third commit, and a test reference that is pointing to the second commit. So Git interacts with files by using references, and it tracks the modifications of files using commits, trees, and blobs. So here it's a resume, a summary of what I just said about the Git objects. So we have the blobs that can be actually found inside the Git, the .git objects database. It has all the contents, and it is name independent because the names are managed by the trees. So the trees contains the structure of the root directory, pointers to other trees that are subdirectories, and file names. The commit is basically a top-level tree, the parent commit, and other configuration files like the author info, the hash values, and everything that we have shown so far. So Git allows for non-linearity because the commit history can be manipulated, and given the fact that each object is fully stored independently from the version, so you always have copies of objects at different versions, this makes branching and merging extremely easy and intuitive, but we need to understand how the history is advanced. And now we can start playing with our local repository that I just created right now. Now, do you have any questions for the moment? So if you have no questions, we can start playing with some references. So if I do git status, Git is very helpful with all the comments that it gives. So for the moment, it says that we are on branch master, that we have no commits yet, and that there are nothing to commit. So branch master, this is the branch name, and it's a reference. We have seen the reference here. It points to a specific commit. So for the moment, there are no previous commits, so it's with what we call a dangling references. The head is a special pointer to another pointer. The head represents the current state of the history in your Git database. To understand this, we need to see maybe a more complex history that I can show on my personal Git project. So the one that you can actually modify and you can check, you can clone, you can play with it from the GitLab hosted at Telecom Paris. So here I am using a command that is called git log. So git log will show you the history of your current project, and it will show it as, you may have guessed, as a sequence of commits. So this is the history. I hope that it is visible in the room. So this is my initial commit, again identified by the hash values. Then you see a sequence of commits, and this is everything that has been done. And then you can see something that is painted with a slightly different color. So here you can already see that there is a branch in my timeline. So from commit, this is a test. I have two different histories. One that is the main, so this is the branch, and one that is experimental. It is another branch. Now you can see that there is a special pointer head that points to another pointer. In this particular case, my head is pointing to the pointer that is called main. So it is a pointer to the branch main. And you can see that head is not at the same level as origin main or origin head. What are those? Well, those are the remote repository, and this means that if I do a git status command, here the git file system understand that my branch is ahead of my remote branch, so of my GitLab repository, by 3 commits. So the head is pointing to some branches that are not yet up to date with the remote repository. Moreover, Git is very helpful because it proposes the changes that can be staged for commit. And to go to this step, we need to understand what is the file status. So a file in Git can be untracked. So if a file is untracked, it means that Git will ignore it. There is no other things that this file, so there is no tracking modification that will be kept into these kind of files. Then a file can be tracked. And if a file is tracked, Git knows about it. Git knows about this file. When Git knows about this file, Git can understand if a file is unmodified, which means that it is already committed, which means that, again, a blob exists in the Git file system. It can understand if the file is modified, and if the file is modified, it can be staged for commit or not yet. So this is your basic working directory. Suppose that you add a file or you modify a file. You can start tracking this file. You do a git add and you put the file into this called staging area or also index. So this means that at next commit, the content of this file will be transferred into the .git repository. So how do you move files from your working directory to the staging area? You do a git add to track the file. How do you move everything from the staging area to the commit status? You do a commit. You can even untrack or remove the file by doing git rm. So you remove the file, and this means that Git will stop caring about this file. So a file lifecycle is something that looks like this. If a file is untracked, it is ignored. Git doesn't know about it. If the file starts to be tracked after you add it, you put it into this staging area. So the staging area is, let's say, the temporary area where the files are stored before the commit. The file is modified, well, then Git doesn't track anymore a modification to this file. It does not need to recreate a new object, a new content for this file. Git knows that you are editing a file, because if it is inside the unmodified area and you start editing the file, Git knows that there is a difference between the current file and the file that is present in its database. You can decide to stage the file again with another add to be submitted for commit, or you can play with your file and you can do modifications and you can do basically whatever you want. So let's have a look at my database. If I do a git status, I know that I am ahead on main by 3 commits. I know that I have files that are not staged for commit. So this is because I did some modifications on my slides. So now how do I track the modifications? How do I use this idea to start tracking the modifications? I can do git add slides. And then when I check git status, I see that I am on branch main. I'm still ahead by 3 commits. And I can modify. So I have modified the slides and I can commit these slides. So when I want to commit the slides, what I just do is git commit. So if I do git commit, it asks me for a message. The commit message can be anything that you want, but I can just write last modifications. And then after I do this, one file is changed, one insertion, 4 deletions. This is what Git is telling me. When I go on Git status, I am on branch main. My branch main is ahead by 4 commits. So if I look again at the log, my head is pointing to 4 commits in the future with respect to what is in my remote repository. So I can finally use some nice push command to just propagate my modifications to the remote repository. For the moment, I am the only one working on this project, so there is for sure no conflict, because I am the only one having access to this repository, but some commits may have a reason, and some errors may have been done. So for instance, you may regret the changes that you have done with another commit. So you can use the command git revert. So it reverts the changes made by other commits. And again, the git status will tell you exactly what those modifications have been. If you want to unstage some files, so you remember, stage the file for commit, it means that they are present in this stage area, also called the index. So when you will run a next commit, an object, a blob, a binary object of that file will be created and stored into the database. But maybe you regret doing that, so you can unstage the file. Or another thing that you can do is that you can change the commit history, so you can move the tip of the branch to another point in time in your timeline. Some of these commands have shared functionalities with others. For instance, git reset can be also used to restore the index, so to completely unstage files. So it overlaps with git restores, and git prefers to have multiple ways of doing the same thing rather than having a single way of doing the same thing. So example that I can do in my repository is that suppose that I add a file, touch file not needed. So I'm creating this file. I check on git status and it says that this is untracked. This is untracked file. I can use git add to include everything into the staging area. So git is very clear in this. So I can do git add file not needed. And once again, when I check the status, well, it checks that there is a new file that will be committed. So the next commit command will create a blob of this file with all its content, etc., etc. But I can unstage the file, and actually Git is very helpful with this. If you want to unstage the file, so if you do not want this modification to be tracked, you just do this, and then everything is clean. Git status, everything is clean, which means that this file is back to being untracked. If a file is untracked, Git doesn't know about it. If you do not even want to know about it, you can just remove it. Or what you can do is a git checkout main. And right now, if the file is not needed, it's still there. And you can easily remove it, and your repository is clean. So nothing to commit, working tree is clean. If you want to check with more details...
Leonardo, I have a question.
Yes.
What happens if you delete the file while it is still tracked?
So what happens if you delete the file when it is still tracked? So let's add it back. So nano file not needed. And then let's add something of this. Git add file not needed. So now the file is tracked. Suppose that you remove it. If you remove it, Git will understand that there is a modification on this file. So for it, it is like you are staging some modification that is the content of the file, and then you are doing another modification that is still not staged. So suppose that now we do rm file not needed. If I check git status, I will see two messages. I will see the message changes to be committed plus changes not tracked. Let's see if it is the same. Yes, it is. So it is changes to be committed because the new file is in the index area. So the content of this new file is being stored in the index, and it will be created by a commit message to the .git database. And then it understands that there is a new modification on this file that is not yet considered. The new modification is that the file is deleted. And Git is super helpful with this. Let me put it in full screen, Git status, so that everybody can see. Git is super helpful with this. So we add two operations. The first operation is to take a file, stage it, and put it in the index. The index is another data structure that is called that is stored into the .git file. So this modification is tracked, and it's ready to be committed. So when you commit, basically what you do is that you copy the index into the list of commits. Let me see if I can show you the .git index. Yes, so the index is here. It is just a file. If I cut x dump, it is a binary file that contains. Maybe I can show the character. Like this. Yes. So it contains exactly the file. So the list of the file forward.png, everything, image. So it's everything that is staged to be reconstructed. So git status will tell me file is staged, file not needed. Then you remove it. It's another change that is still not tracked. And you can keep the change, so you can remove the file, you can restore the file. For instance, if I do git restore file not needed, again, the new modification, so the new deletion, is not considered anymore. But in the index, it is still there. Does this reply to the question?
Actually, when you add it, it makes a copy.
No, when you add it, it means this. So add it, it means I do a modification, the file is modified, and I stage the file for commit. So I put this file in the index. So it is already there.
But
Your file...
The content of the file, is it stored?
It is stored in the index, yes.
Okay.
The content of the file is stored in the index. So when you remove the file, actually the content is already there. The content is already in the index, and so you can safely play with the file. Maybe you can do other modifications. If you are not happy about it, you can update the index. So this is why we say update the index. So the index is a single dimensional data structure. It contains only one modification at a time. It does not contain the history as a commit. So the commit is something that contains every modification and every history backwards. The index is only the last modification that you did on the file if you did the add keyword. So the data structure for
Leonardo, so if you want the intermediate modification, you must commit. Otherwise, you can just go ahead and just edit the file.
Yes, so the simple question is yes, if you want intermediate modifications, you stage the file, so you add and then you commit, and then you modify and then you add and then you commit so that you can always keep track of the modification. This is the simple reply. The more complex reply is that you have some git stash where you can store temporarily the files. Stash is a stack of modifications. So you can stash, and then you can pop the last modification. But we don't do that in this presentation. So yes, if you want to have different versions of the file, maybe commit 1 and commit 2, you modify the file, you add and commit, then you modify the file again, you add and commit. So you have both versions of the file. Otherwise, if you are only in the staging area, you are always locally. You're always locally, and so your new add will replace the previous add. So what we can do with a remote repository is that everything that I have done locally here in my file system, git status, in this moment there is a change to be committed, but we can or we cannot do that. At some point, you may want to collaborate with other people. When you collaborate with other people, what you do is that you can push. So push is basically updating remote references and include all the local history. Or you can pull, so to retrieve others' modification and apply them locally. So if I had other collaborators in my repository, I could have done a git pull here to retrieve all the modifications that other people have done. But for the moment, everything is up to date. You can even separate the retrieving modifications and apply them locally, or fetching the modifications and check if you want to apply them locally or not. This is why we have these two slightly different commands that are git pull, retrieve and apply, or git fetch, just apply, just retrieve without applying. Now, in Git, as you have seen, I typically use just git pull or git push without specifying anything. The full syntax requires an explicit origin and an explicit branch name. So the actual syntax is, for instance, git push alias, that is a URL typically, and branch, that is a master, that is a development branch, etc. So by default, if you don't specify anything, everything is stored into your config file. We can have a look at my config file, that is nano.git.config. And again, it's a file that you never modify manually unless you know what you do. But here you have the aliases of your remote. So in particular, in my remote is origin, and origin has this URL. And you also need to specify, but it is Git who is doing that for you, what are the references that you care about. So the references are the heads, so like the temporary pointer, or the branches that you care, like the main, like the test, like the experimental. And so here it specifies everything that is inside your local copy, but also what is happening inside your remote copy. So you can, for instance, specify another alias for a remote repository that is a backup repository. So instead of doing git push, you can specify git push backup and then on the branch main. You can even specify how to make strange history with different branches, like git push origin dev main. You say that you want to push to the origin branch called main, but you want to add the local branch that is called dev. And here you mess up with the history, so it's never advised to do that. It's much better to keep it simple, so to have everything that is either git push or git pull to the same repository, and just in case, change the branch where you want to push. So we have seen the logs, that is everything that is happened in the repository, but we have also the ref logs that stores everything that happens in your local environment. So for instance, if I do a git ref log here, I have everything, all the advancement that I did with with my head pointer. So the pointer is the last, it's a pointer to a pointer. And so in particular, the git ref logs checks where this pointer has moved. So this pointer has moved for the moment to the checkout, and it is pointing to the main. Here it is pointing to the main. So before it was not pointing to anything because I was doing just commits and I didn't push anything to the remote repository. This is how Git understand if you have local commits that have not been pushed to the remote commits. Here the head is moved into another branch, that is the experimental branch. Here is another branch that is the test branch. And so the ref log stores all the movements that your head pointer has done. So if you clone a repository, this is your first movement of your head. So the ref log is empty. Suppose that now again here, I go to another temporary directory and I clone my repository. I go to tmp and I do a git clone of my repository that is, let me check, git like a pro, should find this, yes. So this is a clone of my repository as it is in the remote version. If I go to my git like a pro, so this is a new directory, it is not my old directory. If I do a git log as I was doing before, I still have the history of the full repository. So I still have all my history that is shared, but my local history, so my head, has not moved for the moment. So ref log is at the 0 position. This is at 0 position because it is the first action that I did on this clone of the repository. So the head has not moved. The head is up to date with main, with origin main, and with origin head. So nothing has changed. So the head is a very flexible pointer to other pointers that can be used to track if any movement has been done. You can move to any point in time by checking out. Checkout just means take your head and put the head into this other point in time. So let's have a look at our log. Let's see that we want to move at this specific point in time. So the point in time that is EBA for AF. What do? You do just git checkout EBA for AF. And then you have a very complex message that says you are in a detached head state. Now, if you understand what the head means, you can guess why we are in a detached head. head is a pointer to another pointer, and in this particular case, if you see the ref log that we have before, this value has no other pointers. In fact, it is a single commit, so your head is detached with all other branches. And the branches is always the tip, is always the last commit. So right now, if I look at my history, my head is here, and it is not pointing to anything particular. My head is here, it is pointing to this hash value, and I can do modifications, I can do whatever I want, but my commits will be lost because they will not be pointed by any other commit. And this is why we get this message of Git saying that you are in a detached head state. So if you want to check out to another branch, you can just specify git checkout pointer name. So your head will point to that pointer. If I want to check out to the experimental branch, I go here and I do git checkout experimental. Now we are on branch experimental. This branch experimental exists also remotely in my origin. And now my history looks like this. So you see the head now is back to being a pointer to a pointer that is pointing to the branch experimental. And a branch can be uniquely identified by its latest commit. So the branch is always the tip of the line. In fact, origin main is the tip of my main history, and branch experimental is always the tip of my experimental branch. So after branching, if a branch diverges, you can either continue linearly or you can try to merge. And when you try to merge, you can do two different kinds of merges. Merging on the same line. So suppose that you are on line main, like here, and then you create a new branch, and this new branch has no other modifications to the branch main except the previous ones. So it is actually a subtree of the same main tree. So in this particular case, test and main have a full shared history. All the history is shared up until to next point. So merging branch test into main just means apply this commit and then apply this commit. So you can do what's called a fast forward. You can directly advance the main pointer to the top. Instead of applying the commits, you can just say, well, let's take the pointer main and let's point it to the same point that test is pointing at. Fast forward is super easy because you do not need to handle exceptions. You do not need to handle merge conflicts. On the other hand, if you have a history like mine that is very diverged, what happens is that here you have a branch experimental. The branch experimental and the branch main have diverged, so they have no common history, but they have a common ancestor here. What happens is that if you want to merge these two commits into the main test, well, you will need to make sure that your new commits are in agreement with everything that happened into the branch main in the meanwhile. So sometimes it can happen that you may need to manually regulate conflicts. And again, Git provides you very nice way on how to do that. And it's very helpful. You can use git diff to check what is happening at a specific branch or at a specific commit. For instance, if I do a git diff with this commit, diff of this commit, it says in a very strange way how everything is happening. It's a diff file, but you can use also external tools, diff tool. So if I use diff tool with this guy here, at some point it will launch merge. and it will ask me everything that is happening with the diff tool. Diff tool in my case is meld, that is graphical user interface version for diff. So here is telling me that your Git file was empty here, and now you are including a .swap. Another thing that I can do is feature. I don't want to see feature. I don't want to see this. I want to see slides.md. Yes. So here meld is basically doing a file-to-file comparison between my version that potentially has a conflict and the version that was pointed at the previous commit. So for instance, here I added this slide. And I removed this part from the previous version. So Git can recover. We have seen how Git can recover from any mistakes. I have pointed to some websites like this one that are unfortunately very explicit in their language. So you can also use safe for work content without swearing words at this website. Dang it, Git. So I think it was nice to have some pointers to what was happening in this website. But I think now I can show you a little bit of my my work flow that I use on GitLab. So in GitLab, actually, we have a graphical user interface, and then I have finished everything. So in my graphical user interface, I use Git to automate via some scripts all my subjects that I write in LaTeX. So basically, how to do that? We can use what's called the CI/CD pipeline. So in particular, Git is very helpful with this. Let me show you a test on how to create a pipeline. If you want, suppose that you have a LaTeX template and you want to automate the production of the LaTeX with your GitLab setup. You can do this. So you can basically build a pipeline. When you build a pipeline, you can use test pipelines like the LaTeX pipeline that you have here. Let me check LaTeX. You can use this template and it creates for you an automated test for making PDFs out of everything that matches some tech, let's say, kind of regular expression. So you can use this script, and every time that you use this script, a new artifact will be created that contains automatically all your PDFs. So in my pipeline that I have here, so this was the LaTeX template pipeline, but I want to show you my actual pipeline. So it was here. In my actual pipeline, what I do is that at every push that I create on one of my LaTeX text file, what happens is that I will automatically have an artifact with all the PDFs that have been produced, plus all these PDFs will be pushed into my Moodle learning system in Telecom Paris. Instead of playing with this pipeline, I will show you another pipeline that uses instead a much simpler interaction that is with Mattermost. It's the equivalent of Slack for open source purposes. So Git like a pro. Now what happens is that, let me see if I have something to commit. Yes, let's commit this file. Git commit, this is an experimental file. Experimental file. Yes. And then let me do a push. When I do a push, I will automatically create a message for this channel, and everybody that is log to the channel, it will receive a message of my commit that is being pushed by me as an author, and with this particular hash value. I use this also to push to social networks like Mastodon, and therefore, every time that I do some activity, a GitLab event somewhere is generated, and it is creating exactly the message that I want. Messages can be customized, of course, and this is just to show that Git is much more than a collaboration tool. It can be used for plethora of activities. I lost my slides, so I have to redo that again. I think I can do it on localhost. So just one moment. I can do this, and I can do this with localhost, so that I can conclude my presentation. So, can I do end? No, I cannot do end. So it should be about here. So to summarize the talk, I think before knowing what Git can do, it's important what Git should not do. So in fact, I voluntarily skipped some concepts like stash, rebase, or other complex workflows, because the idea is to keep it simple. And you have seen that when you understand the basics, Git is just a way to advance your storyline one commit at a time, and being able to recover by no matter which kind of mistakes, or to be able to merge no matter which kind of paths. So by keeping it simple, you still keep Git's features like CI/CD integrations, like Webhooks, like local hooks that unfortunately we didn't have time to explore today. And so I want to finalize with some remarks on the presentation. I think books are really helpful. Figures help a lot. And hands-on is just much better than just reading. Another thing that I want to highlight is that while I prepared this presentation, ChatGPT help was completely useless, because there were some level of technicalities where, doing something, since Git allows you the way to do many things with many alternative ways, suggested examples were either wrong or not functional. So I do not advise using ChatGPT to learn how to use Git. And another thing is that the Git implementations, unfortunately, are much far away than the interface that they really say to provide. One of these differences is, for instance, on how the code, the server-side code of Git was used to interact with my scripts. So on the paper, it was written that something was being done, but in reality, I mean, at least our version of GitLab was doing something else completely. There were some errors. So I'm not a developer, so I'm no one to say that this code is badly written, but I was very surprised. So I skipped some parts. Maybe for another advanced session we can have a continue of this lecture. But I think that the basics are out there, and with this, I think I can finish my presentation. So I hear nothing. And if you have any questions, please feel free to ask them. Otherwise,
Yes,
happy holidays.
well,
Yes.
I have many questions, but
Yeah.
so usually when you start using it, you mess up your local repository. So how can you fix it easily? Like how can you recover everything in one simple command?
Very well. So for this, you go to the website with a swear word. you go that. So given that if you have remote history that is still coherent, so suppose that you clone a repository, you do something, you mess up something and nothing works anymore. If you have this, there is one single thing that you can do, that is this thing. You simply remove everything and then you clone again your repository. That's guaranteed to work.
So
This is,
that is the way I do it, but
yeah. Well,
not something best.
so this is not the best exactly. So this website is very helpful because it says if you want to do it in the Git way, well, you can do this. You can do this. You can do this manually. You can fetch the origin. You can check out to the master, and you can do a Git reset to the origin master. So everything that is untracked, all the directories, everything will be removed, and then you clean your repository to make sure that everything is locally coherent with the remote state. So the Git way is this, but again, if you have an easiest way, you can do that. But in reality, you actually need to do these three things. If you already are up to date with the origin, you check out to the master, you reset your head state with what's happening into the master, and then you clean.
Okay, so I think another class about CI/CD would be helpful.
I think so.
It seems everything was hidden. In particular, I guess for some automation, you need to provide password or credentials of some sort.
Yes, yes. Well, in fact, Git is already equipped for doing that. So you have secrets, you have URLs. So if I can show you briefly my pipeline for my LaTeX things. So let me get the TP subjects. So this is a private repository. In my private repository, I have all my templates for my labs, for my exams, etc. So in my GitLab CI/CD, I have two stages. I have the build and upload. So for the build, I just build. I use LaTeX. So I use LaTeX. It's a script that I wrote for
Okay.
LaTeX. For the upload, I just simply upload with the CURL the specific files to the website, and the website is here, but the secret is stored in variables. So here I am using the APIs of Nextcloud because our website of Partage is Nextcloud. So it says if you want to update a file, you just create a request, put with the URL of your files. So in particular, I want it to be stored in labs download. And then my authorization bearer is this variable that is hidden. It is a secret, and you can share this, you can store the secret in the settings of your repository.
Okay.
So you can also create access tokens. You can create one-time tokens. You can, let me see if I can visualize the pipeline, because you can create very complex pipelines.
No, no,
Um,
but it can be for the next class.
it can be for the next class, yeah.
I need to practice before.
No, but once you use it, it's also very helpful because some scripts will pass, some other will fail, and then notifications can be used for failing. So the pipeline editor, maybe it's like this. Yeah, view pipeline. So for instance, in this case, the pipeline is a graph. Normally you have stages, but you can create one stage that requires another stage. So in this particular case, upload requires build, because otherwise uploads and build can run in parallel. So job dependencies, it's like this. Show dependencies is this one that requires this. So
no other questions, so thank you.
thank you. Okay, so happy holidays, everybody.
Happy holidays.
Happy holiday.
Thank
Bye-bye.
you.
Bye bye bye.
Uh,